Carboxylic acids are the only functional group we study in introductory organic chemistry that are true acids. If you dissolve a carboxylic acid in water and measure the pH, you'll find that that water is acidic. It's not surprising that the fact that carboxylic acids are acidic dominates their chemistry. So we're going to find ourselves talking about acids and bases, and it would be worthwhile making sure we're all on the same page about definitions and the fundamental principles of acids and bases according to the Bronsted Lowry theory. It's a very simple definition that these guys use. Acids are proton donors, and conversely, bases are proton acceptors. Put in the form of an equation, we're saying the following. A base, put together with an acid, will undergo a proton transfer reaction that is reversible, so there's an equilibrium established. In terms of our arrow pushing, we track pairs of electrons making and breaking bonds, and the base has a pair of electrons to share with the proton. When the proton is removed from the acid, a pair of electrons is left over. And so as we picture that proton transfer, we see this pair of electrons being used to form a bond with the proton as this pair of electrons stays with the A-. And if we're looking in that reverse direction, we picture a pair of electrons from this base here forming a bond to reform the acid while this other partner gets its electrons back. I want to emphasize that this is an equilibrium process, and a true equilibrium will be established if this is allowed to continue for a while. For many proton transfer reactions, the equilibrium is established very fast. For others, it's slower. You will have already figured out that I used B here because this is a base, and this is the acid partner. This is the conjugate acid of that base, and the A- is the conjugate base of the acid. To emphasize the fact that the base and this conjugate acid on the right-hand side are coupled, let me put them in a special color. And to emphasize the relationship between this acid and its conjugate base, let me put them in a special color. Now this is an equilibrium reaction, and you would guess that the equilibrium isn't very often 50-50. It's generally shifted to one side or the other. In fact, the position of equilibrium is shifted from the stronger acid to the weaker acid. The stronger acid pushes to the weaker. Now, if we're interested in knowing in which direction that equilibrium is shifted, we're going to need to know something about how to determine whether an acid is strong or weak, which acid is stronger and which acid is weaker. Let's take a look at some definitions that will help us think about this. Acidity is measured using the pH scale, and pH 7 is defined as neutral, neither acid nor basic. You know that in plants and animals, physiological pH is very close to 7. Values smaller than 7 are defined as acidic, and larger values correspond to basic. And smaller pH values mean more acidic. So as we talk about solutions that have low pH values, we're talking about more acidic solutions. There's a very similar scale that's used to talk about the strengths of acids themselves. This is defined as the pKa value. The strengths of acid are measured using this value, and smaller pKa values mean stronger acids, just like smaller pH values mean more acidic solutions. So what is a pKa? Well, the pKa is equal to the value of the pH when there are equal amounts of the acid and its conjugate base in a solution. Put in terms of an equation, we're saying that if we have a solution of an acid, HA, in water, there will be an equilibrium where we have formed the conjugate base of that acid, an H3O+. The pH of the solution that makes these concentrations equal defines the pKa. And the amounts of acid in its conjugate base will be equal at lower pH values when the acids are stronger. So as the acid gets stronger and stronger, it will still protonate water at more and more acidic solutions. And what determines whether an acid is really strong or not? Well, we can measure the pKa value and know whether it's stronger, but what determines whether it's stronger? What makes one stronger than another? Well, there could be several factors that account for this, but there's one primary factor that we can focus on that lets us understand the relative strengths of most acids. Take a look at this series. I want to look at some organic compounds and their pKa's. Alkanes and alkyl groups, amines, alcohols, and carboxylic acids. In approximate numbers, the pKa values of these groups are as follows. 60, this is a very large number, and these are very weak acids. 35, this is also a large number, also weak acids. Alcohols, 15, not strong acids by any means, and carboxylic acids, 5. So you see that the pKa values are varying dramatically, and we know that the lower pKa values mean stronger acids, so the carboxylic acids are much stronger than others. Let's see if we can account for this. In each case, the base removes a proton and leaves a negative charge on a specific atom. It turns out that there's a very good correlation between strengths of acids and the stability of these conjugate bases. The stability of the anion we're forming determines the strength of the acid itself. This is a very important observation. So now all we need to do to determine the strengths of acids is understand what makes a conjugate base more stable. And there's a key principle. The better the conjugate base is able to accommodate the negative charge, the more stable it is. And there, the more stable it is, the stronger the acid. So the ability of a conjugate base to accommodate the negative charge is the determining factor in most cases regarding relative acid strengths. So let's take one look at this and see if we can understand what's going on here. As we go down this list, we get to stronger and stronger acids because the electronegativity of the atoms is increasing, and more electronegative atoms better accommodate negative charge. And when you get to the bottom two, the negative charge is on oxygen in both cases. Same electronegativity. There's a second principle at play. In the bottom case, the conjugate base of the carboxylic acid, that anion is resonance stabilized, so it is better able to accommodate the negative charge. This resonance structure also puts the negative charge on oxygen. And in fact, it's identical to the resonance structure we had written. And when two resonance structures are very similar, they both contribute substantially and contribute to greater stabilization. So the top three conjugate bases are differentiated from each other on the basis of increasing electronegativity. And the bottom two are differentiated from each other on the basis of resonance. So there it is. We can understand the order of the strength of these acids by looking at the conjugate bases and seeing that as we go down the list, the conjugate base is more and more capable of accommodating the negative charge. And in the case of carboxylic acids, it's capable of accommodating that negative charge both because the negative charge is on oxygen and because there are two resonance structures. As we look at carboxylic acids, their relative strengths, and their chemical reactivities, the principles I've talked about here regarding acidity and relative strengths of acids will be important.